Hello my friends, my name is AB, and in this video we're going to talk about why do we need quantum mechanics? Why do we need it? So by the end of 19th centuries there were many phenomena which were not explainable with the help of classical mechanics. So the new theory was needed, and indeed that theory was quantum mechanics. So one was blackbody radiation. Blackbody radiation. So before going to blackbody directly, we'll talk about how the objects are heated. So not how, what happens when the objects are heated. So if you just heat any random body object, okay, instead of heating, if you just shine a light upon it, then this object would absorb some amount of radiation, some amount of light, and it will reflect a little of it. Okay, so if you just, if you do the same with black body, what happens? That black body, that it will absorb everything, all the kind of radiation incident upon it. It will not reflect anything. It will just absorb it. So when this black body is heated, you would observe, it will give off many, whole range of frequencies, and when this emission spectra were observed, they found something weird, something unusual. They found like this black body was giving off a whole range of frequencies. Well, this is frequency, and this is amount of frequency. So they found that there was a particular frequency, this is at, let's say, 1200 Kelvin. So there was a particular frequency which was present in maximum amount of that radiation given off by black body. And when this body was heated even further, they found a shift in the peak frequency. So there were many attempts to try to solve this black body radiation, but no one was able to solve it. And finally in 1900, Max Planck solved it. He said that the energy transfer will always occur in quantized manner. And so what it means is that when the object is given energy, it will absorb it in discrete manner. It would absorb some amount of energy, and then keep on absorbing that same amount of energy, and it will also give off the energy in the same manner, in discrete manner. So let's say this black body is kept at 1200 Kelvin, then it will not give off radiation in continuous manner. It's kept at 1200 Kelvin. It will not give it in continuous manner, but it would do so in discrete manner. It would send out tiny packets of energy, of the energy. You might be knowing that when the object is kept at constant temperature, then it's at thermodynamic equilibrium. It will absorb some amount of radiation from surrounding, and it will also give off the radiation. So that's what's happening here. Just only one thing is added, that this transfer will occur in quantized manner. In it would give and take tiny bundles of energy, and Max Planck called them quanta for plurals and quantum for singular. Okay, and the new era was started with the lucky guesswork of Max Planck. And moving on further to another effect, which was photoelectric effect, which was photoelectric. Yeah, people tried a lot to explain this phenomena, but no one was able to explain it, because they just didn't think that how can these waves, which has no mass, no momentum, can transfer energy to particles. So in 1905, Einstein he just carried forward the idea of Max Planck, that energy is quantized, is not spread over the wavefront of the waves incoming. So first we talk about what's photoelectric effect. So if you have a metal, and then if you just light it up, I mean, if you just shine light upon it, then what would happen? The 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 electrons present in the around electrons around the nucleus of metal, they would get energy from these waves, and they would just get freed by these incoming waves. So what happens? The energy of these waves, energy of radiation, is used for, first it would be used for delocalizing that electron. So you have to free the electron from the effect field, from the field of nucleus. So the energy would be consumed there to get it freed, and then the remaining energy would be used uh, for kinetic. It will be used as kinetic energy of that electron. So energy of radiation will be used for freeing electron from nucleus, and the remaining would be given as kinetic energy. So Max Planck said that the energy is quantized. The transfer of energy would always occur in quantized manner. So with his theory, with his guesswork, he set a new formula, and that formula was E equals to h nu, where E is energy, h is Max Planck's constant, which is this Planck's constant, and it equals to 6.626 into 10 raised to minus 34 joule second. And nu is frequency of radiation. Frequency of radiation. And Einstein used this idea to give to explain photoelectric effect, and he said that the energy of radiation would be, of course, h nu, and it would be used for freeing electron. That was given as work function plus k of electron, and this work function is nothing but the energy required. So simply you can write it as h nu naught, where nu naught is the frequency, which is a particular frequency required to free this electron. Let me change this color. Okay. And in more technical experiment, such as this one, here electrode is attached, connected to a battery, and then if you just, then this is anode. First of all, this is anode. This is anode, which is positively charged, and this is cathode, which is negatively charged. And then if you shine light on the anode, then they found that despite of having negative charge on cathode, the electrons were going towards cathode. They found a flow of electron in opposite direction. And yeah, here energy transfer is occurring from radiation to the particles, that is electron. So Einstein proposed that the radiation, the light, is not a wave but a particle, and he called them photons. Photons. And the opposite was observed, that yeah, there was one more phenomena known as X-ray emission. I hope the spelling is right. Okay, the X-ray emission. So what happens if you force the electrons to go through this vacuum, then the opposite would happen. What will happen when the electrons on the cathode, they go to the other side? The work is done on those electrons by the voltage applied, and as they go through this vacuum, when they reach anode, they would just emit rays. They would emit radiation, and that was found to be, that was named as X-ray. So 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 the energy transfer was occurring between radiation and particles. So there was just confusion that whether this radiation is in particle nature, or it is just simply waves. But but yeah, and then that's where the basis of quantum mechanics was set. And oh, oops, one more thing. Here it should be field of nucleus or simply atom, from freeing electron from atom, or field of nucleus. And yeah, that's why this new theory was built. Okay, oops let me change the paper. So because of this unexplainable phenomena, this new subject was brought into picture: quantum oops mechanics. And you just know that takeaway message will be: energy is quantized. Energy is quantized. Energy is quantized. So energy would be shared, transferred, only in tiny bundles of packets of energy. And the another one will be the light. The light carries it possesses both the nature. Light is both wave and particle. Okay, then I would see you in the next video. In the next video, we will talk about the confirmation of quantum mechanics, how it was tested so hard, and it was confirmed that yeah, indeed, this these things happens. So okay, see you in the next video. Let's spread knowledge. Let's spread knowledge. See you soon.